Years after its discovery, Cygnus X1 had caused a profound division in the astronomical community. Something was roaring from the depths of the galaxy. A powerful source of X-rays that, at its core, invisible to us, could be concealing a body whose existence we had been denying for decades. Einstein's equations, in their intrinsic elegance, hid a new conception of the universe. Connecting the mathematical world with the physical general relativity forever transformed the view of space and time. But initially, neither he nor anyone else was aware of the dark secret contained in his formulas. Mathematics predicted the possibility that, after the death of a massive star, space-time could collapse into an infinitely small region. That the architecture of the cosmos could fracture at a point, giving rise to an invisible monster with the power to drain all the light from the universe. Pushed to the limit, Einstein's equations predicted the existence of what were baptized as black holes. Guardians of the darkness that hid in their hearts the place where all paths end. A singularity where the laws governing the behavior of the cosmos collapse. Where mathematics crumble and the quantum effects of gravity reign. Like a dark well in the universe, everything is drawn by the gravitational power of the singularity, faster and faster, like a river accelerating in its course. At every moment, escaping the stream becomes more difficult, until a point is reached where it no longer matters how fast you swim. A cascade has formed in the fabric of space-time. Nothing can escape anymore. That point of no return is the event horizon, a region around the singularity from which not even light can escape. The boundary between the universe we know and that hidden in the unknown and dark depths of a black hole. And although everything seemed too strange to be true, that spring of 1971, we had to accept its existence. Measurements taken on the star in the Cygnus X1 system showed that it was orbiting the invisible object with a period of just 5 days. A speed that could only be explained if that unknown body had at least 6 solar masses. The possibility that it was a tiny neutron star was ruled out. There was only one option left. It had to be a black hole. A beast that, by devouring a blue supergiant star, was creating that bright source of radiation. 6,000 light-years away, we had captured the first evidence of its existence. They had always been hidden under the shadow of their own darkness, but we had found them. Black holes were a reality, and the world of astrophysics focused on revealing the nature of the kings of darkness. In this context, the theoretical physicist and American astronomer Jacob Bekenstein wanted to investigate the relationship between black holes, information theory, and entropy. 3 concepts that together, in a place where physics collapses, were going to lead us to uncharted territory. When we talk about information, entropy relates to the lack of knowledge or predictability, the measure of the amount of information lacking before its reception. Therefore, applied to those dark monsters, the entropy of a black hole represented the amount of quantum information of everything that has fallen into its heart, that has crossed the point of no return. Aware that it was impossible to read the information inside a black hole, as nothing, not even light, can escape its depths, Jacob focused on determining precisely that, how much entropy it contains. Logical thinking told us that the amount of entropy of a black hole would be proportional to its volume, just as the amount of coffee in a cup is proportional to the volume of that cup. But against all odds, mathematics revealed just the opposite. Bekenstein's equations showed that in the case of black holes, and unlike what happens in any other body in the universe, the amount of entropy is proportional to the surface area of the event horizon, not its volume. Something strange was happening with them, but at that moment, we were unable to see it. The idea was so counterintuitive that it was immediately relegated to speculation. However, the course of that story changed 3 years later, in 1974, when a young British physicist published a study that would forever change our view of the Guardians of Darkness. Stephen Hawking had shown the world a phenomenon he himself had baptized as Hawking radiation. A new era of astronomy had begun.
Las ecuaciones de Einstein nos enseñan que en cierto modo la energía y la masa son lo mismo. Puedes convertir masa en energía, igual que puedes convertir energía en masa. Esta innegable idea, demostrada con la ecuación más famosa de la historia, es igual a mc², llevó a Hawking a preguntarse qué ocurriría cuando estos fenómenos tienen lugar alrededor de un agujero negro.
Around one of these beasts, hell awakens. Gases at extremely high temperatures and powerful magnetic fields. The energies near that corrupted heart are immense. And inevitably that energy manifests itself in the form of particles. It transforms into mass. From the quantum vacuum, pairs of matter and antimatter particles are constantly emerging, which we call virtual particles. In the sense that, due to the instantaneous annihilation between matter and antimatter, they never behave like real particles. Their existence is so ephemeral, the annihilation is so rapid, that they revert to energy in a tiny fraction of time, as if nothing had happened. This quantum phenomenon is happening incessantly around us with no implications for the universe. But when it takes place in the vicinity of a place where all laws collapse, where our knowledge collapses prey to a fractured heart, everything is different.
Cuando esa creación de partículas virtuales sucede en la frontera del horizonte de sucesos, es posible que una se precipite hacia la singularidad y que la otra escape. En ese momento no se puede producir una recombinación, no hay una aniquilación, y esa partícula que en principio estaba destinada a desaparecer se convierte en una partícula real, y eso es precisamente la radiación de Hawking.
Over time, particle by particle, black holes lose mass. They evaporate due to particles emerging from the quantum vacuum. An incredibly slow emanation of particles that would, over inconceivable timescales, cause the Guardians of Darkness to consume themselves and disappear. The discovery of this phenomenon catapulted Hawking to worldwide fame, perhaps being the greatest contribution to science in his entire life. Furthermore, Hawking radiation confirmed all of Bekenstein's research on the entropy of black holes. But it was precisely by exploring the implications that this had on quantum information that he and other scientists realized what the radiation, in its deepest sense, was hiding. His theory implied that the black hole is evaporating through particles emerging from the quantum vacuum. These particles do not contain any information about their initial state. Therefore, when its moment comes, when it has evaporated and radiated all those particles that have nothing to do with what the black hole actually is, it will leave no trace of what its singularity has devoured. Information, a priori, was being lost. But this conflicted with one of the tenets of quantum physics. Hawking's radiation violated the law of conservation of information. The problem that would obsess the physicist for his entire life had just emerged. The information paradox had sprouted from the depths of the beasts.
Las leyes de la cuántica nos dicen que cada partícula aporta una información sobre sus propiedades que no puede perderse jamás. Y la información en su sentido más puro es la distinción entre las cosas. La lógica nos dice que cuando arrojas algo a un agujero negro, esto desaparece para siempre. Pero desaparecer implica perder información, perder distinciones. Y sin distinciones pierdes una capacidad de predecir que sin ella hace que toda la física colapse.
The information paradox was a cry from the universe, an indication that something in the foundations of our knowledge was failing. We had to find the place where that lost information rested. And against all odds, that path was going to lead us to an unknown empire, a realm hidden behind the pillars of reality. In the late 1960s, the world of physics was focused on finding a theory that could fit gravity into the quantum model, the only fundamental interaction whose nature we were unable to explain in that invisible realm, at the smallest scales of the universe. The quest for a theory of everything, a framework that would unify all the forces of the cosmos into a single and elegant equation, had begun. But after many failures, it was a young theoretical physicist named Leonard Susskind who presented the world with the best approximation of that dream. Inspired by music and imagining that, just as the vibration of the strings of an instrument determines the nature of sound, perhaps the same principle could be applied to the universe. That all the reality around us, in its most elemental nature, could be reduced to strings vibrating in the quantum world. Tiny strands, one-dimensional threads that by vibrating in space-time and depending on how they do so, cause the various particles of the standard model to manifest. They were reaching for the simplicity everyone yearned for, the elegance contained in that quantum empire. Assuming the mathematical existence of closed strings, they could describe the holy grail of that crusade. The string loops would behave exactly as expected for the graviton, the hypothetical elementary particle that would transmit the gravitational interaction. For the first time, a model was explaining the quantum existence of gravity. String theory was born. A new era of physics blossomed within those equations. From the outset, the model was promising a hope to find the long-awaited theory of everything. But its weaknesses soon emerged. String theory imposed different restrictions on the universe. The model did not work for a four-dimensional space-time, those that we can perceive and where our reality unfolds. For the mathematics to hold, it needed to conceive a cosmos of 10 dimensions, with 6 extra spatial dimensions that we haven't detected. Likewise, independent models were required based on the closed or open nature of the strings. Restrictions that inevitably led the theory to split into 5. 5 string theories, each valid in its own conception, but seemingly disconnected. And if we couldn't even unify the theory into one, the dream of describing the theory of everything seemed impossible. In the late 70s and 80s, many approaches were made to reconcile the 5 string models, but none seemed to make significant progress. At least not until the 1990s, when several physicists, particularly the American mathematician Edward Witten, began discovering a subtle network of connections between the theories. Dualities that linked the 5 models together by introducing an additional theory of 11-dimensional supergravity to the scene. All the theories became connected, transforming the chaotic model into a single framework, more simple and more elegant. The 5 string theories had unified into what Witten named the M-theory. The Physicists' Conference in 1995 made a significant impact on the community, which had been trying to decipher the string puzzle for decades, sparking a deep interest in those dualities. Mathematical phenomena of seemingly unrelated theories that fundamentally, in their most elemental nature, represent the same physical reality. It was precisely the dualities of string theory that inspired an Argentine theoretical physicist to delve into the model that seemed destined to describe the true heart of the universe. Juan Martín Maldacena had planted the seed of a principle that would forever change our view of reality. Maldacena imagined a set of objects within string theory called branes. Multidimensional strings that behave like membranes, serving as anchor points for one-dimensional strings and at the same time as spaces embedded in higher dimensions. The three-dimensional branes would be extremely close to each other, practically overlapping, and the strings attached to them, presenting mathematically proven scale invariance, could vary in length and energy without altering their physical properties. Under certain conditions, he saw that the resulting membrane structure resembled a 3 plus 1-dimensional spacetime, like the universe we live in with 3 spatial dimensions and 1 temporal, from which also emerged a field theory due to the interaction between branes. Having that scale invariance property, it was what is known as a conformal field theory. A quantum theory like the one from which the standard model of particles derives, but with added supersymmetry. Maldacena had added a spatial dimension that incorporated that invariance. The 3-dimensional space had become a 4-dimensional one. While the original theory's space was flat, this, with the 4 dimensions, showed a curvature that, as he showed, was negative. A hyperbolic space that, in the field of cosmology, appealed to an anti-de Sitter spacetime. A universe that, unlike ours, which is positive, has a negative cosmological constant. Maldacena demonstrated that around these anti-de Sitter spaces, what we could consider the limits of that universe, there would exist what was defined as a conformal boundary. A border with one dimension less than everything inside the cosmos. In essence, he had developed a gravitational theory for anti-de Sitter space and another for the boundary of that space. 2 theories linked by a duality. An equivalence between 2 theories in a different number of dimensions of space, in which, moreover, in that higher dimension, gravity naturally emerged. He had a complete theory of quantum gravity. The duality or AdS CFT correspondence for anti-de Sitter and conformal field theory was born. The world for the first time heard about what would be named Maldacena's conjecture. A door whose existence we were barely aware of had opened before us.
Maldacena publicó la teoría en 1997 y con las posteriores confirmaciones matemáticas todo parecía indicar que las dualidades eran viables incluso para un universo como el nuestro. En esta forma más general, sin la abstracción que pedía la concepción original, esta correspondencia pasó a conocerse como el principio holográfico.
The holographic principle is the idea that the physical reality we are familiar with, our reality in 3 spatial dimensions, could be a projection of more fundamental laws operating on a 2-dimensional surface surrounding us. A 2-dimensional covering beyond the borders of the observable universe from which our 3-dimensional reality emerges. In this sense, similar to how a light hologram can create realistic images that appear to have depth from a flat piece of plastic, the principle uses this analogy to describe what could be the cornerstone of the cosmos. The place from which everything emerges, a surface that contains the true physical laws governing the behavior of the universe. Creating a reality that seems real but is actually just a holographic projection of the processes taking place in that region.
La conjetura de Maldacena, la mejor aproximación a una teoría completa de la gravedad, nos estaba diciendo que en esencia todo lo que vemos, todo lo que sentimos y todo lo que somos en nuestras 3 dimensiones, junto con la percepción del tiempo, podría ser una ilusión, un holograma, una proyección de lo que ocurre en un campo de 2 dimensiones, más allá del universo observable.
Everything would be stored on the borders of the cosmos, far from the place where everything happens. The holographic principle was telling us that the real physics is in a place infinitely distant from our universe. That both gravity and the existence of an extra dimension within the box would be just an illusion. A projection within space-time. Maldacena demonstrated that all the laws of the cosmos can be completely explained from what happens on a plane with one less dimension and laws different from ours, but that store all the information to encode us. The physicist's publications and conferences caused a whirlwind within the community. His conjecture was collapsing all the conceptions we had about the universe. But no one could deny that with it, suddenly all of physics worked. Everything came together, advancing toward the dream of a theory of everything.
Estaba abriendo la puerta a grandes reflexiones sobre la realidad y la existencia. Si el universo real existía en dos dimensiones, un plano infinitamente alejado de lo que experimentamos, todo incluido nuestra vida, sería una ilusión. Pero no podíamos ignorar lo que las ecuaciones nos decían. Teníamos que seguir ese camino, sin importar el lugar al que podíamos llegar.
The mathematics had shown us that path. That the real universe could exist in a flat bubble beyond the horizons of space and time. And only dark entities could give us the answers we needed. It was time to return to the place where all paths end. "15 years after the theorization of the holographic principle, Maldacena's original article had already surpassed 10,000 citations, proclaiming itself as the most cited publication in the history of high-energy physics. The mathematical foundations of the AdS CFT correspondence were solid, but tangible evidence was lacking, that link to the reality we can perceive. And after a long time navigating in the dark, the answer came from the place where the story had begun. The event horizon of a black hole could be the perfect analogy for the horizon of the universe. If they took that boundary of the dark monster as a representation of the two-dimensional fabric that Maldacena's conjecture posed, perhaps they could bring the holographic principle closer to our tangible reality. General relativity showed us that as you approach a black hole, time progresses more and more slowly, until at that event horizon, the point of no return to that path of darkness, time essentially stops. From the outside, everything freezes at that instant. Therefore, they could conceive a vision in which nothing actually ends up falling into the singularity. Nothing reaches the heart of the beast. The event horizon with that stopped time would be the true frontier. A shell that in the framework of holographic theory would be a two-dimensional membrane, encapsulating all the information of everything that has tried to venture inside the monster. When a body is swallowed by the black hole, the information of each and every one of its torn particles is imprinted on the surface of the event horizon. Right on what we considered an imaginary boundary, there could be a two-dimensional sphere that somehow contains the quantum essence of everything it has trapped. All the information of objects, once three-dimensional bodies, is preserved, encoded in the two-dimensional surface of the black hole. An eternal archive is maintained on it. We are not losing anything. Nothing disappears from the universe. The holographic principle, for the first time in decades, was preventing the guardians of darkness from undermining the foundations of quantum physics. The information paradox was resolved.
La información que portan los objetos no se pierde. Aunque sea impresa sobre la superficie del horizonte de sucesos de un agujero negro, esta sigue estando disponible. Y si este fenómeno es posible sabiendo que las leyes del cosmos son universales y que lo que sucede alrededor de un agujero negro debería aplicarse a todo el universo, estábamos llegando al lugar que necesitábamos. Tal vez esos monstruos oscuros nos estaban revelando la naturaleza ilusoria de la realidad.
Just as black holes store the information of each and every atom they have captured, the information of everything in the universe could be recorded on a two-dimensional bubble that surrounds us. A cosmic hard drive that contains the data of everything that happens within it. And although intuition might tell us that the surface encompassing the universe could not contain all the information of its volume, everything is happening in a realm where the counterintuitive prevails. And on the Planck scale, the numbers show that indeed you have enough space on a two-dimensional surface to specify everything that happens in the universe. The mathematics of black holes were supporting the theory of the holographic principle. But if we truly wanted this conception to rewrite the foundations of cosmology, we had to find observational evidence. And although it seemed impossible, there was a moment in the universe where we could find it.
Desde que empezamos a describir su naturaleza, vimos las inevitables semejanzas entre los agujeros negros y el Big Bang, el instante en el que la semilla del universo germinó. Todo surgió de una región en el espacio-tiempo donde las condiciones eran tan extremas que toda nuestra física se derrumbaba, igual que en el corazón de un agujero negro, un lugar donde los efectos cuánticos de la gravedad reinan, al que llamamos una singularidad.
Understanding this elegant connection between the dark monsters and the birth of the cosmos, the next stop on the path seemed evident. The trail of the holographic principle led us to that moment where everything began. Simulating a Big Bang under the framework of the holographic principle, the universe would simply start as a disk of information. A plane that exists solely and exclusively in two dimensions. From there, as the information it contains interacts and therefore complexity increases, a new dimension sprouts. The two-dimensional disk brings forth a spherical reality in 3 dimensions. The hologram is born, and the space-time we know has begun its odyssey to create the wonders of the universe. Once again, the numbers revealed that what seemed to be a purely speculative scenario was solid based on the equations. But if true, this holographic birth of the cosmos should have left echoes of its existence. Imprinted scars for all eternity in the light at the edges of the universe.
Nuestra única esperanza se encontraba en una radiación ancestral que impregna todo el universo y que procede del instante en el que 380.000 años después del Big Bang, los primeros fotones fueron liberados de esa opaca bola de plasma que era el cosmos primigenio, unas cenizas del nacimiento del espacio y del tiempo, el fondo cósmico de microondas.
Thanks to the mission of the Planck telescope, in March 2013, we had obtained the most complete and detailed image of the cosmic microwave background to date, the farthest in space and time that we were able to see. An ephemeral radiation that comes from the moment when light was born. Running simulations of the expected temperature variations with that holographic Big Bang, scientists found very promising similarities with the Planck image. The holographic principle fit the observed pattern in the cosmic microwave background. It was the first time that the idea proposed by Maldacena showed subtle echoes of its real existence. The suspicions were strong enough to initiate a direct search. To immerse ourselves in the quantum realm to observe, from within, the nature of the cosmic hologram. Under this pretext, a year later, in 2014, Fermilab initiated an unprecedented project, the development of the most sensitive laser interferometer in history, a device theoretically capable of detecting fluctuations in space-time, a noise in the very foundations of reality, that was due to the holographic nature of the universe. The holometer, as it was baptized, charges a laser to a very high energy, and then splits it into 2 beams. Each of them, at the same instant, is shot through a 20-meter conduit, at the end of which it encounters a mirror. The mirrors reflect the lasers, which return to the detector. The principle of the machine is based on the idea that any holographic disturbance in the quantum realm could move one of the mirrors by a trillionth of a meter, a minute change that the holometer with the return of the lasers should in theory be able to perceive, offering us echoes of that authentic reality.
A día de hoy el equipo sigue ajustando el dispositivo, y aunque no haya garantías de ello, si algún día somos capaces de captar esas fluctuaciones cuánticas, unas vibraciones en la tela del espacio-tiempo debidas a la proyección de una realidad bidimensional más allá del universo, estaríamos ante uno de los descubrimientos más importantes de nuestra historia.
But in the midst of that wait, an unexpected clue came from the cold and dark void of space, showing us that perhaps the evidence we had always been looking for rested in the firmament. In the islands of light that inhabit the oceans of the universe. In 2016, a team from the University of Amsterdam, led by Dutch theoretical physicist Erik Verlinde, initiated an investigation into a property of that holographic principle that they believed could explain one of the great mysteries of modern cosmology. In the 30s, Swiss astronomer Fritz Zwicky studied the behavior of the Coma cluster, a large galactic cluster with over 1,000 islands of light, analyzing the movement of galaxies and comparing the data with values expected by mathematical models. He saw that there was 400 times more mass than expected. Galaxies were moving much faster than they should, at least if we relied only on the mass of the stars at their core. There had to be something else, an invisible matter that we were unable to see, but that was exerting a profound gravitational power on the galaxy. A hypothetical entity he dubbed dark matter. Considered for a long time a mere speculation, a theory conceived solely to force calculations whose foundation had to be wrong, it was not until the 70s that the definitive proof arrived. American astronomer Vera Rubin, studying the velocity curve of spiral galaxies, showed that the rotation speed of stars did not decrease as they were farther from the galactic core. The finding only made sense if indeed something was providing gravitational cohesion to the galaxy. There had to be a halo of invisible matter 9 times more massive than the visible portion of the island of light. It was an observational certainty that galaxies were immersed in a colossal cloud of dark matter. Since then, the consensus about the existence of this substance that we cannot perceive, feel, or see is almost absolute. After all, it is the piece we need to describe the gravitational pillars of galaxies, the structures that give meaning to the universe. However, the University of Amsterdam team believed that the fact that no matter how hard we tried, we could not even capture echoes of its existence was a sign that dark matter has never existed. What has always been behind it is the holographic nature of the cosmos itself. Erik's equations indicated that the seemingly impossible movement of galaxies is an intrinsic property of the holographic principle. It is not dark matter that gives cohesion to the island. It is the bubble beyond cosmic horizons that holds the pillars of light. According to the conjecture, from the 2-dimensional galaxy encoded on the holographic surface emerges a framework that extends throughout the universe, anchoring itself in the 3-dimensional projection and maintaining the movement of the stars. We don't need dark matter. The foundations of the hologram were the piece we had been looking for so long. Still, if they wanted to rewrite decades of scientific thought, they needed to find evidence that justified their intuitions. The hypothesis predicted how the intensity of gravity would vary across the galactic disk if it were a holographic universe. A change that, thanks to gravitational lenses, we could perceive. Studying about 35,000 galaxies, analyzing how their gravitational power curved the light of millions of other islands of light behind them, they finally saw that their theory matched the observations. A more elegant solution to a mystery whose resolution had always depended on dark matter. An indication that the true nature of reality is hidden in that holographic principle.
Cuando en 2017 publicaron el artículo, el principio holográfico se convirtió en todo un fenómeno, inspirando a científicos de todo el mundo a seguir persiguiendo rastros de esa realidad elemental, esperando a que llegue el día en el que a través de ese holograma estemos más cerca de entender qué somos y qué lugar ocupamos en este espacio y en este tiempo.
Because this quest has always been based on it. to find a path that would lead us from the darkness of the guardians of darkness to the light of the gods of the galaxies. To that place we have always wanted to explore. The pillars of reality. The nature of a universe that has found in us a way to understand itself,